Okay, so let's continue. Last time we sum of all these diffusive ladder diagrams and to form a so-called diffusive propagator, capital D of Q, which is the geometric summation of all the ladder diagrams for this Anderson localization problem. And after summing over all the ladder diagram, this is the D of Q is given by this U squared over 1 minus U squared D0 of Q, where D0 is the two ladder basic diagrams that need to be summed over, and U is defined as mv squared. And then last time we derive after here this D0 of Q diagram, and then the last time is given by this separation of this integration over p prime variables in terms of the angular integration and energy integration, the epsilon and d phi. And we plug in this propagator G plus and G minus that we obtained earlier. And remember that for G plus, there is a minus sign in front of this imaginary part of self-energy. For G minus, this is a plus sign. So today we will continue finishing this calculation. And to actually make progress, we need to perform the contour integration like before, right? So we need to generalize this, the epsilon integration, say originally between plus and minus infinity, right? So, okay. So now we need to generalize this to complex plane, where this epsilon is generalized to a complex variable z. Here that we need to perform a contour integration, and we need to choose the proper semisphere, the contour. And the way that we choose the contour, it's obvious that we need to choose this upper hemisphere. Okay, so if we choose the lower hemisphere, then we don't get a convergent result. You could check that pretty easily. And once we enclose the upper hemisphere as a contour integration, and we simply just pick up the pole, and in the upper hemisphere there's a single pole right here, which is at Vf dot q plus I over 2 tau, and in the negative imaginary axis there's another pole which we don't care, which is at minus I over 2 tau. So we only enclose the upper hemisphere and pick up the pole and residue at a pole, and this is the result after we finish this integration over the epsilon, and that's it, right? But we need to perform the remaining angular integration over d phi, and again, to do that integration, we also need to generalize the the angular variables phi to the complex variable z over a unit circle, which is defined right here. So we need to generalize this angular variables phi to the unit sphere in the complex plane, which is defined by z, right? So which is e to the I phi. So the real part of the z is actually cosine phi, and the imaginary part of z is sine phi. Okay, so d phi in this new variable is given by dz over iz. So now we can actually perform such a contour integration around the unit circle defined by this complex variable z. And then again, there are two poles. If you solve these pole positions by demanding that this denominator should vanish, and remember that this cosine phi is given by what e to the I phi plus e to the minus I phi, which is z plus 1 over z, and we define this prefactor v of q as a and 1 over tau as b. Okay, so you plug in this and you find this pole positions, and there are two poles. One is inside this unit circle, and another is in the negative imaginary axis, which is outside of the circle. But of course, we need to pick up the pole inside the circle, and then you simply just do the algebra, and this is the final result. Okay, so the final result is given by this 2 pi over I times 1 over the square root of this Vf squared q squared plus 1 over tau squared. Okay, so, and let's take a short break. When we come back, and we will continue making some simple approximations in the small q limit, and we'll see what this diffusive propagator becomes finally. Okay, so let's take a short break. Okay, so let's finish this diffusive propagator. And as we know already that this d0 of q after this contour integrations is given by this expression, where you have this square root of this form in the denominator. And for the convenience, we define this mean free path L, which is given by Vf times this mean free time tau. And the diffusion constant, capital D, is defined as Vf squared tau divided by 2. So, and you'll see in just a moment that there is a factor of capital Q, which is momentum transfer in the denominator of this d0 of q. And so, yeah, you could simply just Taylor expand this, the square root, function in the denominator, and to the leading order, you get this 2 pi n, which is density of states at the Fermi level, times mean free time times 1 minus capital D times q squared tau. All right? Okay, so now you simply just plug in this d0 back to this full diffusive propagator, capital D of q, and here, so you plug that in, you get this denominator, and in the numerator, this is just a constant mv squared. But this prefactor, this 2 pi times density of states times the mean free time tau times v squared n, and which is simply just constant 1. Because previously, when we derive the self-energy, imaginary part of the self-energy, and define this mean free time, we already obtained such a relation between 1 over tau and this density of states and this impurity concentration and impurity potential, right? So previously we obtained such a relation, and if you simply just move this tau on the other side, and you get exactly this prefactor, right? It sounds like a magic, but it's not a magic. So indicates that this complicated product of all these parameters simply gives you simply just a constant 1. And then you could just rewrite this capital D of q, in terms of this mv squared divided by capital D q squared and tau, because this 1 cancel with that 1 over here. And this minus signs, flip this minus sign, you get the plus sign. Okay, so this is the final result. This diffusion propagator gives you this 1 over d, 1 over capital D, and also 1 over q squared dependence, and 1 over tau dependence in this diffusion propagator. So as we'll see in just a moment, that when this momentum transfer capital Q vanishes, or in the small q limit, and this diffusion propagator diverges, because it's actually in this form of the 1 over q squared, and as a result, when q vanishes, this diffusion propagator diverges. And that's what I said earlier, that the backscattering, which is precisely this diffusion propagator, implies the backscattering term dominates the whole thing, the electron transport, and shows a dramatic effect. Okay, so let's just analyze the dramatic effect that comes from the divergent diffusion propagator. So we could simply just plug in this diffusion propagator, capital D of q, back to this electrical conductivity tensor that we already defined. So we just could focus on this longitudinal component, sigma xx. And this is given by the constant, which is some kind of a residual conductivity, plus this small deviation of this sigma xx. Suppose we apply this external vector potential, right? So linear response theory tells us that delta sigma xx is actually proportional to this bubble, right? So this diffusion bubble. So this wavy line, which connects this upper and lower parts of the bubble, is precisely this diffusion propagator, capital D of q. And remember, this capital D of Q is a sum over all such ladder diagrams, particle-particle channel, and we need to plug in what we have right here, the diffusion propagator here, right? So this be inserted right here. Okay, so let's do it, and you will find later that when we plug in this diffusion propagator, capital D of Q, right here in this bubble, and the final results for this delta sigma XX will show the divergence when this dimensionality is actually 2 or 1. And so let's do it right now. So we simply just write down this expression for the diagram, this conductivity diagram, up to linear order in this external vector potential. And we also plug in all this electron propagator, including the self-energy corrections, this G plus and G minus that we already derived previously. Okay, and again, we need to integrate out all this internal degrees of freedom, which is capital Q in a d-dimensional space, and also the angular part, which is cosine square phi, because in this delta sigma XX, we pick up this px right here, another px right there, so altogether you get px squared, and the px is m times vf times cosine phi, so you pick up the cosine square phi right here, right? Okay, and there. So this is G plus, and G minus, and right, this is G plus and G plus right here, and G minus and G minus. Remember, when we have such a bubble diagram connected by this diffusion propagator, we already performed two kinds of twists and turns of this electron propagator, so that this G plus is connected to G minus right here and also in the bottom. Okay, so let's finish the job. Again, so we need to perform the contour integration. So this contour is made of this upper hemisphere, and there are 4 poles, 4 simple poles, and 2 of them are inside of the semicircle, and another 2 are in the other side of this negative hemisphere or lower hemisphere. So let me just indicate this pole position. So let's just collect all these residues, at these 2 poles, and so these are these 2 contributions from these 2 simple poles after plugging the residue. Okay, so let's just keep simplifying this expression. So okay, so if you simplify these 2 terms, you'll find that this is given by this factor times that factor. And in the small q limits, you could simply just forget about this, because this q cancels that q, and this q square in the denominator could be neglected at this point. But remember, there's 1 over q squared right here in the diffusion propagator, which we have not included, because we only included the other part of this, say, the epsilon integration, right? So remember, this is simply just the epsilon integration. Okay, so let's take a short break. When we come back, we'll combine everything and get the delta sigma XX. And you'll see that this is proportional to, again, the d-dimensional q vector integration times 1 over q squared. So you will see in just a moment that this, the whole thing is proportional to this integral, right? And with a minus sign. So this is a very important sign right here, which tells us that these corrections due to the diffusion propagator actually gives you the negative contributions to the electrical conductivity, which is proportional to 1 over q squared in an integral, right? So again, in low dimensional, meaning a 2-dimensional or a 1-dimensional system, we'll see immediately that this correction, the negative correction, is actually infinity, which actually overcompensates this finite electrical conductivity that you start with, meaning the correction is really negative and singular. So this negative and singular contributions coming from the backscattering, really suppress all the electrical conductivity from the start. So that is the phenomena called the Anderson localization. So let's just comment on that in just a moment. Okay, so let's look at the final result. Okay, so after combining everything, this delta sigma xx shows the negative contributions to the electrical conductivity with a factor like this. But though these prefactors are not important except the final one, this integration over this momentum transfer vector q with 1 over q squared. So you could easily see that for a two-dimensional, say, thin film, metal thin film, and this integration over the q right here leads to the logarithmic divergence, right? So if this is the two-dimensional integration over this q vector, and the leading term is given by this dq over q, and the lower upper limit of the integration, the smallest value for the q and the largest value of the q, right? So, but in terms of the length scale, this corresponds to the cutoff, say, momentum cutoff, which is 1 over your, say, lattice constant. And the smallest q value corresponds to 1 over your length scale, the system size. So combining everything, you get this logarithmic divergence factor. And so this lattice constant right here is a little a. Sometimes you could approximate this as the, say, mean free path, which is the smallest distance that you can find in your system, right? So, but the most important part is the logarithmic divergent factor when the system size, capital L, becomes very large, or in the thermodynamic limit, so that capital L divided by the small l is really infinite. Okay, so but you carry this prefactor minus sign right here, so this indicates that the total sigma, the total conductivity, sigma xx, is actually sigma 0 plus delta sigma xx, right? But the delta sigma xx reports to you this minus times the log divergence. Okay, but we know that correction cannot be infinity because the correction should be very, very small. So along the way that you approach the thermodynamic limit, this negative log factor already suppress all this residual finite conductance, that conductivity in your system. So sigma 0 is already gone. Before the log term diverges, this sigma xx total is already 0. Okay, so this is 0 when the system approaches the thermodynamic limit. So you need to be aware of the fact that you cannot have the negative conductivity right here by definition. So you cannot overcompensate this positive value of the sigma 0 by this minus infinity of this delta sigma xx, right? So it is unphysical. Okay, so the fact that this is a logarithmic divergence factor just tells you that all this finite positive sigma 0 will be completely suppressed. Okay, so by the time that this log factor becomes infinity, the total sigma xx is already gone, right? So when the total sigma xx is 0 and you don't correct it anymore because the system is totally insulating. Okay, so you do not get this minus infinity as your total sigma xx because that is really unphysical. So the thing that we calculate here is the perturbative estimation of this corrections to this sigma 0, and the correction should be small. It cannot be infinity. Okay, but that divergent singular correction, which is a negative sign, tells us that this total sigma xx is actually 0. Okay. So which means that in this thermodynamic limit in the two-dimensional thin film doped with random impurities, the total conductivity along the x component is actually 0, which means that electrons cannot have any coherent transport. Okay, and this is precisely one limit of this Anderson localization phenomena. Okay, so it sounds simple, but it's highly non-trivial in the sense that we start with a very naive-looking impurity scattering potential, which is delta function, and we assume a very simple, uniform white noise distribution of that impurity, and we start collect of the self-energy corrections and also this vortex correction based on the Green's function method, and finally we arrive highly non-trivial conclusion that this innocent, naive-looking impurities doped randomly into the metal for the low-dimensional systems, and this totally destroyed the coherent electron transport. Okay, so, and the reason, as I mentioned many times, is precisely because of backscattering. This, remember, this diffusion propagator is actually the backscattering processes where these two electrons sitting on opposite side of the firm surface and exchange a small momentum, and when they get scattered, these two electrons exchange their momentum. Okay, so which means that this electron come in, and when it bounces back, it is almost total reflection of the electron, and which we say this is the backscattering because electrons got backscattered by this impurity potential. Okay, so I suppose this is the end of this Anderson localization phenomena and the Green's function approach to understand this Anderson localization problem. So of course there are still many other things that is really classic theory of Anderson localization, but we don't have time to discuss that scaling theory of Anderson localization and this kind of conductivity that follows this sort of a renormalization group flows, and as the system actually increases to infinity, and this electrical conductivity actually follows either a logarithmic divergence or even more singular divergence, and in three-dimensional systems you get the metal to insulator transition, right? So in 3D, so this is not homework, but this is just final remark. You have both this metallic and insulating ground state, and they are competing. Okay, so whether the ground state is metallic or insulating depends on this impurity concentration, and if the impurity is highly concentrated, and the system will become an insulator. But if you have not enough impurity in your system, and the metal is still a metal at ground state. So we indeed get MIT, which is metal to insulator transition. And this is precisely what happened in the experiments for three-dimensional metal doped with the random impurities, and experimentally people already observed such a metal to insulator transition. Okay, so in other words, this phenomenon is real and has been observed in experiments. And the understanding of this metal to insulator transition is precisely what we discuss right here. So we calculate this conductivity bubble by including the self-energy and vortex corrections, and in different dimensions we could see different results. Okay, so let's take a short break. When we come back, we will start a new chapter, which is electron gas with Coulomb interactions. And we say goodbye to this Anderson localization problem, which we discussed quite a long time, and we will return to the solid state one that you are familiar with, that Coulomb interacting electron gas. We can actually modify the Coulomb potential by the same way. Okay, and then we'll study this dielectric constant and dielectric functions using the Green's function method. Let's take a short break. Okay, so let's start a new chapter, which is electron gas with Coulomb interactions. And we know very well this Coulomb interacting electron gas describe many solid state materials, mostly metals. And we know that in those materials we have a neutralized and uniform charged background, which means that the total charge is zero. And you know that these charged particles in these materials consist of ions, positive charged ions and negative charged electrons, and this charge from these ions and electrons got cancelled exactly, so you get a charge neutralized system. And the Hamiltonian is simply just made of two parts. One is the kinetic energy term, which comes from this kinetic energy of electron gas, and also the potential term, which in this Feynman diagrams is in terms of the electron scattering by the Coulomb potential, and the Coulomb interaction is given by this dotted or dashed lines right here with a strength in this momentum space 4 pi e squared over q squared. And this Coulomb interactions mediate electron-electron scattering, where the two electrons carry, say, momentum k and k prime. They got scattered, and after scattering, this electrons carry momentum k now becomes electron with k plus q. Another becomes, say, k prime minus q, and little q is the momentum transfer. Okay, so in the second quantized fields, we could represent such Coulomb interactions in terms of the four operators, two daggers and two non-daggers. Okay, so you could immediately see that this k and k prime are initial electron states carrying momentum k, k prime, and they got scattered by exchanging a momentum q with photon, or this Coulomb term, and after scattered, the electron carry k plus q and k prime minus q over there. Okay, so you need to sum over all possible incoming electron states, k and k prime, where k is not equal to k prime. Good, so we need to calculate this consequence of this Hamiltonian, and we need to calculate the self-energy of the electron propagator, and we also want to calculate this correction to the Coulomb interactions by this electron-electron interactions by Coulomb. And we know previously that this single electron propagator in this Matsushibara frequency and momentum space is given by this G italic, which is 1 over I omega n minus this bare electron kinetic energy plus the chemical potential and minus the self-energy. And we know that self-energy is made of this a single bubble or a balloon attached to a solid line, which is, again, so we already argue and find that this is simply just a shift in the chemical potential of the electron, and we neglected this self-energy diagram, and the remaining part of the self-energy is this one. But of course, we have other corrections beyond this one particle irreducible, which is the correction to the, say, the vortex correction, which is the correction to the Coulomb potential itself, which modify this dashed line right here. So we will talk about that in a moment. And we could perform this analytic continuation from this Matsushibara frequency to the real frequency. And in the retarded part of the Green's function, which is capital G plus, and we have this 1 over omega minus the bare electron energy and minus the self-energy. Okay, but the self-energy in general shows the real and imaginary part. So we could actually combine the real part of self-energy with the bare electron energy. And by doing so, we define this capital E, which is the total electron energy, kinetic energy, which is the sum of this bare electron energy and the real part of the sigma. And of course, we have this imaginary part of the self-energy, which is in this I times gamma form. Okay, so we will address this later, right? So this gamma defines this electron lifetime, also this scattering rate. And if we have the finite gamma right here in this electron propagator, and you could Fourier transform this GQ omega to GQ t, and in real-time domain, this capital G shows the exponential decay, right? And the decay constant is given by gamma precisely. So, which means that the electron loses this coherence and correlations as time goes by. So gamma is really 1 over lifetime of electron quasi-particle lifetime. Okay, so that's just the basic background. So in the following, we will try to correct this Coulomb interaction. And before that, we could define electron effective mass based on this sort of a firm liquid formulation. So let's take a short break. Okay, so let's try to analyze these implications of this electron, say, excitation spectrum, and so-called one particle excitation energy for a single electron. And we know that this is capital E as function of momentum q, and also the energy capital E of q, or omega. And this is sum of the spare electron energy and the real part of the self-energy of electron. And from this formulation, we could define so-called electron effective mass from this free electron gas theory. And electron mass is the constant appearing in this quadratic dependence of this kinetic energy term. Q squared over 2m, where this m refers to this free electron mass. Okay, but here in this so-called renormalized electron energy, we can also define such a effective electron mass. Okay, which means that the electron gets heavier by including this interaction effects. but we could still define such this mass, which appears as the q squared term in this electron energy. But now the prefactor right here, which is actually the prefactor in front of the q squared, is no longer 2 times the free electron, the bare electron mass. Instead, this is m star. Okay, so we could evaluate this m star, the ratio of m to m star, which is defined as this partial derivative of the capital E respect to the bare energy, right? So if the capital E is the same as the bare energy, then this is simply just 1, because if the capital E is actually epsilon 0, then this partial derivative forwards to you simply just 1, which means that in the free electron system, there's no Coulomb interaction effect. Then the electron mass is simply just m. Okay, but in the presence of the self-energy or this electron-electron interactions, and this derivative is not trivial. Okay, it's not simply just 1. Because you know that the real part of sigma will contribute to this differentiation, because this sigma depends both on this q and energy. Okay, this capital E is the same as that capital E appearing on the left side of the equation. As a result, you get 2 different contributions, and one is the derivative of this bare energy with respect to this bare energy, which is 1, which is precisely this 1 appearing at the first term, but there is a second contribution coming from the self-energy, and the self-energy contributions to the effective electron mass shows 2 different contributions. One is the derivative of the real sigma with respect to this energy, or q. Another is with the omega, because this sigma is a function of both parameters, q and omega, but we need to take care of this derivative, 2 different independent variables. One is momentum q, another is the omega, but the omega should be evaluated right at this Fermi level, okay, which I call this capital E0, where you should evaluate this derivatives of this real part of sigma with respect to the omega, and evaluate this omega right at the Fermi level. And of course, this q should also goes to qf, the Fermi momentum. So you could rewrite this kind of the 3 terms in terms of this ratio. In the denominator, you get 1 minus the partial real part of sigma partial omega. And in the numerator, this is 1 plus this partial real sigma partial epsilon 0 of q. So if you Taylor expand this denominator, you get precisely the 3 terms right here. And this ratio is evaluated right at the Fermi momentum and Fermi energy. So you can see very clearly that this derivative of this real part of sigma with respect to either this epsilon 0 of q or this omega do not vanish in general. As a result, you get enhancement of the electron mass. Okay, so that's just some of these basic formulations of Fermi liquid, and we will analyze this so-called the vortex correction in just a moment. So we know the electron shows the finite lifetime, tau, which is defined by this imaginary part of self-energy. And we should also bear in mind that this Coulomb interaction also pick up these corrections to this vortex, or this Coulomb strength of the Coulomb potential. For example, in the self-energy diagrams, we could study the effect of this so-called vortex correction. So this is the corrections to this, say, dashed line, which is a Coulomb interaction strength due to the electron Coulomb scattering. Okay, so diagrammatically you could see this from this. Okay, so suppose you just look at this, say, this part marked in red, and this is the second order Coulomb scattering diagrams that you can imagine from this perturbed expansion. But if you somehow connect this 2 solid lines or 2 electron propagators, and you form exactly this bubble inside this red box. Okay, so if you just simply look at this red box, and it tells us that the dashed line get a corrections, right? And this correction is in the form of the bubble, and this bubble inserted in this dashed line represents a correction to the Coulomb interaction strength due to this electron-electron Coulomb scattering. Okay, so the electron-electron Coulomb scattering will modify electron self-energy, but at the same time, it should modify the Coulomb potential itself. Okay, so, and this is the more important effect. We will consider this diagram in the following, and we will analyze the summation of all such bubble diagrams inserted in this interaction propagator, and so it will modify this Coulomb propagator, which is a correction to the Coulomb interaction strength, and these corrections will lead to a very well-known phenomena called the screening. Okay, so the screening of the Coulomb potential comes exactly from this type of corrections, and we will see in just a moment. All right, okay, and then we could define this dielectric function, electron dielectric function, epsilon, which is a function of both Q and omega. Okay, so solid state 1, you are familiar with this epsilon or dielectric constant, but only when omega vanishes, right? Okay, or even Q equals 0. So Q equals 0 and long range, in the long wavelength limit and static limit, omega 0 limit, this epsilon is just a constant, which is famous or well-known electron dielectric constant in metals, and which could be evaluated even in a semi-classical approach. But in general, if you consider this dielectric function, which is a function of the Q and omega, then this cannot be done without Green's function approach. But this epsilon's function of Q and omega is a measurable quantity that you could do in your lab. Okay, so you simply just use the AC electric or magnetic field, AC field, and or just magnetic field, and you could use this EM wave to actually probe this metallic materials, and so that you could get this epsilon as a function of, say, momentum transfer and also the frequency of your AC field. So this is the measurable quantity, but how to understand the behavior of the epsilon as function of Q and omega needs the knowledge of the Green's function approach. Okay, so the understanding of the epsilon as function of Q and omega beyond the introductory level of the solid state physics. Okay, which is precisely what we will discuss right here. Okay, so let me just tell you that this is the dielectric function is actually proportional to some correlation function, especially the imaginary part of the correlation, and this imaginary part of the correlation is what we call the density-density correlation function. So if you calculate this correlation between this electron density at different time and space and perform the Fourier transformations of that electron density correlation and take the imaginary part, and that precisely corresponds to this epsilon Q omega. So we will come to that point later, but this is just kind of outlined what we will discuss later, right? So I guess we have discussed part of the self-energy previously, but we haven't discussed this. It's called vortex corrections, or the screening of a Coulomb potential. Okay, so I think that's probably enough for today. We will continue, say, analyzing this so-called electron polarization, which is vortex correction to the Coulomb potential in the next lectures. And we will formulate a similar diagrams like Dyson type of equation to analyze this vortex correction. And we will derive this epsilon as function of Q and omega next time. All right? Okay, great. So I'll see you next Monday then.